Huh? Yeah.
We're waiting, and I hope we all have a lot of energy after last week, which was not very intensive for the course. So if you were not able to attend, you can look on the last week presentations for this online. So they were tape recorded, and I hope they're visible. So we need to wrap up to complete our studies of Hartree-Fock theory, Hartree-Fock method, and become ready to next method, which is density functional theory. And I don't know, do we have classes next week? Okay, good. So you have time just to accumulate energy for next subject, and it's time to finish something right now. So when we hopefully meet tonight in the lab, and next and coming Thursday, we should also complete an important step in our practical training. And there is a list of subjects that we should present if you have steam and wish. And I have put some names there, but it is just optional. If you not better, okay, thank you. So please reconsider the list, especially after tonight session, because we should evaluate how much we go forward in accumulating practical skills, and maybe redesign a little bit the schedule so that we do not try to present things that we didn't learn. And the subject number 3, which will be presented here for sure tonight. I will do my best to show all details, but it looks as a hard, big topic, and maybe we can split it into several volunteers, throwing in some ideas. Okay, so this meeting, this lecture shouldn't be too much of intellectual challenge for you guys. So you just sit, relax, listen. There will be a little bit more than average equations, but they are spacious, they take space, but they're not hard to perceive. Do not be too much alert. In case you do want to have some second opinion, I did a last minute Xerox copying of one page from textbook, and I will scan and send it to SDSU too.
Thank you.
So this is very oversimplified summary of what will be delivered today. It is just a summary of Hartree-Fock theory. So we do consider on several previous lectures that we do have quantitative models of molecules and materials, and we were successful in splitting them onto nuclear part and electronic part. And for the electronic part that we are elaborating right now, we assume that nuclei are frozen, but there is an important feature that we need to take into account carefully. There is an electron-electron interaction. And we agreed that number of degrees of freedom, number of electrons, dimension of wave function is too big. It never can be done neither analytically nor computationally in full. Therefore, one tries to neglect something to simplify something, and we are trying to project multi-electron wave function onto single electron picture. So in this way, in this direction, we are having a ladder of objects more and more complicated. We start with atomic orbitals, then they serve as a building blocks for molecular orbitals. Then, based on atomic orbitals, one composes SD, which states not for South Dakota but for Slater determinant. And then out of Slater determinant, one composes the total energy. And then we are going to look into this arrow. How one builds molecular orbitals and how they enter the overall schematic. Because those are one electron orbitals, but they need to carry, to reflect properties, the nature of a molecule that has multiple electrons. So what we are going to do, we are going to switch from continuous molecular orbitals, which depend on position of only one electron, to set of discrete coefficients. This orbital number I, could be some index for expansion coefficient. So we go from continuous to discrete. It's also coefficient for molecular orbital. And we are establishing equation that controls, that governs those expansion coefficients for molecular orbital. As soon as we do have this equation, we can pursue overall schematic and find Slater determinant, find total energy, and if the total energy is not perfect, we can reshuffle the procedure over and over again until it gives satisfactory result. We need an equation which will generate set of molecular orbitals reflecting electron-electron interaction. So in this way, we will briefly review what are basis functions, and then we will check on 5 little concepts, each represented with an equation, which could be merged together, and they will serve to build an equation that will satisfy our goals. This will be the equation that we are going to derive and to analyze is referred to after the name of its designer, so it is a single word equation. And as the very last slide, we are going to look onto plan how one would approach encoding, programming of Hartree-Fock theory into computer. We're not going to do it ourselves. Thousands of people did it before, but we should have an idea what is going on. Okay, those are just a couple of slides to add human factor into the lectures. So this is, I'm not expert in history of science. I just took 2 minutes per person to take information from Wikipedia. So about this person Hartree, I found that he was involved in building first computers, and some of them were on the abacus level with some rolling wheels somewhere here. And he made some enthusiastic statements that computers will be very helpful for progress of science. And another person that contributed to developing of Hartree-Fock theory, he emphasized that it should be specific usage of Slater determinants rather than simple products of orbitals. And I have very tiny relation to this person. So he was a graduate school advisor of this person, and I was sitting in his lectures a year before he died, and well, it was complicated. I do not remember anything from his lectures, but there is a little connection. Okay, so let's go forward. Okay, those are our goals. Just set up an algorithm that we are going to discuss at the very last slide. And now we need some equations that will be used in this algorithm. So we already discussed that many electron wave function is composed of single electron molecular orbitals. And the key feature of all our effort, of all necessity to spend more than one lecture on this method, that one builds up one electron problem that carries multi-electron interaction. So one considers all but one electrons creating background charge distribution and acting on a single electron that we're working with. And from intuitive consideration, it should repel. All this background charge should repel single electron out. But there is an additional potential which is attractive, and it doesn't have classical analogs, so it corresponds to the process that 2 electrons, one that we are considering and another one electron from the background, are swapping their places instantaneously. So this is not something one can imagine, but if added into the theory, it gives good predictions of real-world materials. So a little review of molecular orbitals composed of atomic orbitals. So atomic orbitals are centered on each ion, and when one composes those orbitals as function of position, one can also represent them as a set of coefficients, where indices indicate which molecular orbital we are speaking about, and which ion on which orbital on which ion is contributing there as a basis function. So not very important for basic ideas, but practically, some people focus on the following property. So that orbital, a molecular orbital, can be represented as an expansion over different number of atomic orbitals, and atomic orbitals can be represented in a form of different functions, more or less successful. And overall idea of playing with those basis functions is that by increasing number of those functions and increasing the way they are presented, one can get an increment in precision of everything, precision of the methodology, and predicting more realistic description of properties of molecules and materials. Okay, so let me briefly overview two very different types of basis functions. So the one that is typically used in chemical software is in software designed to describe molecules, and is used to write basic books on computational chemistry, is centered on atomic orbital, right? Because there are a few molecules and there are some hydrogen-like orbitals. So they are for s orbitals. Like if you have ion position 1, ion at position 2, and then there is this position of electron minus position of ion. So electron is localized around first ion. So it is S-like orbital in very simplified one-dimensional picture. If one does same picture for electron localized around second ion, so it's decreasing exponentially depending on the absolute value of distance. And the next p-like, well, actually p orbital, it has a factor of difference between distance of electron and ion in front. Therefore, this Gaussian decay of the wave function amplitude swaps the sign if one crosses the position of ion. And if being drawn in 3 dimensions, this does form p-like orbital. If there are polynomials of higher order in front, one gets the rest of d, f orbitals, and so forth. So this is valuable and helpful for atoms and molecules. But if one is looking onto big chunks of solid state, of materials like semiconductors, metals that follow crystalline structure and that do contain a lot of ions, another type of basis set is more helpful. So instead of having functions that are centered on each ion, one takes the functions that are spread over the whole space. So they are homogeneous, but they correspond to electron traveling with different velocity, different speed. And those functions are used as basis. So each quantum state or molecular orbital is represented as a superposition of several states corresponding to motion with different velocities. And those are known as plane waves. Exponential, velocity times position, and the real part of the thing looks like periodic function. So final result shouldn't depend on basis one uses. But in some cases, usage of one or another basis can be more preferential. So a little technical detail, how the Gaussian software is written. What is the oversimplified basic idea behind it? So numerically, those functions do have a sharp cusp. So it is not a good thing. There is no derivative at this point. So one uses a trick. One replaces exponential of absolute value of difference in distance into Gaussian decaying function. So square of difference in distance. So these functions are not equal to each other formally, but on far elongations, on far distances from ions, they decay in a similar way. And using set of Gaussian orbitals instead of atomic hydrogen orbitals gives substantial improvement in algorithmic way. So the program is called Gaussian because it does use these functions instead of this one. It doesn't use precise atomic orbit. Yes? Between this and this. So here we have a power 1. Here we do have power. So Gaussian draw it. The one with power 1 is very rapidly at the point where the r equals 0. The Gaussian function has a much smoother behavior in this point. So near the ion, those functions are substantially different. But as we go away, they start to behave in a similar way. Okay, so our goal is to find expansion coefficient. We do need to represent molecular orbitals in discrete way because we are going to set up commands for computers, or someone will do it for us. Make an algorithm represent everything in numerical form, and continuous functions are not the best thing for computers. So we are going to build an equation for those coefficients. So represent each molecular orbital as a set of numbers and establish an equation for those numbers. Repeating what our goal and what we want. So we are going to discuss each of these 5 features and represent each of them in a mathematical way. So the repulsion of a selected electron by the rest of electrons, then this antisymmetric feature, the attractive type potential corresponding to exchange of electrons. And then we will elaborate on something that will replace Hamiltonian operator. It will be some operator of energy, but since it is not exactly energy, it is not exactly Hamiltonian, and it is used in Hartree-Fock theory, one calls it Fock operator. So one molecular orbital. And then we are going to find all molecular orbitals as eigenvalue, eigenstate problem for this Fock operator. But for practical need, we will introduce the overlap operator. Then we also need a specific matrix element for electron-electron interaction. So there is nothing new. We already know all mechanics, all science behind this, but now we are going to be a little bit more rigorous than yesterday. Okay. So we are representing our single electron of interest is focusing on its position index labeled by letter R lowercase 1, and the rest of electrons are considered as depending on R2. And there could be much more electrons. Here is just over simplified notation. So there are more than one electrons, but we are looking only on one electron. And we are looking on some operator that corresponds to this potential, attracting the, not attracting, repelling the single electron from the rest of electrons. So from the total energy from multi-electron Hamiltonian, we can extract this term, which will include, let us say, density of the rest of electrons in space location R2. Then distance from our electron of interest to this position of the rest of electron, and integration over this position where interaction takes place. So this mechanism is referred to as Coulomb, because it corresponds to classical Coulomb interaction, and it is an operator that affects wave function depending on of our electron, depending on one. So this Coulomb interaction is often represented as a picture. So there is a branch of science where people are tired of writing formulas, but they need them. They replace each formula with a picture. So this area of science is referred to as quantum electrodynamics, and one of the founders was Feynman, and he offered a way to replace equations like this and even more complicated with some kindergarten-style pictures. So here is representation of this formula in this diagrammatic way. So one wave function is represented as an arrow. If it is a cat wave function, is a normal wave function without any symbols, then it goes from left to the right. If it is a bra wave function, star, then it is an arrow moving in the different opposite directions. So we are having, if you want to find the total energy, we need to add another pi1 star, and there will be total 4 components. So and the interaction, the Coulomb propulsion or some other sort of interactions are represented by wavy lines instead of arrows. Here we are looking on the something at position 1 interacting with something at position R2, this 1 over distance, and this is represented by a wavy line. So since we are performing integration over everything that depends on R2, we can say that this is a little black box. And our electron is hitting some sort of wall, which we do not know what it is internal structure. It's hitting something and get bounced back. So the integration here corresponds to the crossing everything which is inside. But this term is normal. One can understand it based on common sense and classical science, Newtonian mechanics and electromagnetic field without quantum theory. The next term appears due to the fact that total wave function has antisymmetry. It is based on Slater determinant, and therefore the total energy gets an additional term corresponding to this permutation of indices. And the structure is, mathematical structure is very the same, but it does reflect the fact that this operator is acting on wave function of electron placed in position 1. But as a result of acting by this operator, one is getting another quantum state, another electron at this position, at this position 1. So the one electron from the background and one electron that we are discussing are swapping their places. And here is the way how to reformulate in mathematical way, how to enter it into the equations. And here is the diagram. So at position 1, first electron interacting with second electron, but then instead of bouncing, they are swapping their places. And it is, if you want to make it as a black box, we see that we start with electron in one state, and then we end up with electron in another state. This is corresponding to exchange mechanism. And it is a legitimate question. If you are talking to someone doing computational chemistry and you want to give this person a hard time, you can approach and say, what do you do to take into account exchange effect? Is it important for your system? And most of people are feeling it as a hard time and trying in approximate way, but it is not precise. But this effect is important. Okay, so we are almost, not almost done. We're just 2 steps in our list of concepts. Let's go forward. Next is Fock operator. So this is something that should affect one electron molecular orbital. And since it does affect one electron molecular orbital, it does contain trivial terms, the kinetic energy of electron and potential energy of interacting of this single electron with ions, the nucleus to this electron 1. But in addition, there are terms that correspond to interaction with background distribution of the rest of electron. The terms that correspond to Coulomb and exchange. But those terms have been integrated over the positions of the rest of electrons, and they are formally one electron operators. So the whole thing acts only on one variable. There is one electron operator. And main advance, main achievement of Hartree and Fock that they did establish the understanding that eigenstate of such operator is the best possible building block to form Slater determinant. So if you find eigenstates of this operator and build multi-electron wave function out of them, it will be in a reasonable proximity to ideal multi-electron wave function. But here we pay very small price. Instead of solving for very big number of degrees of freedom, we just solve one electron quantum mechanics problem. Okay, a little rigorous thing, but it is not complicated. So, in case we are using the basis of atomic orbitals, which is very good for molecules, we know that those orbitals that are localized on a selected ion are orthogonal to each other, right? But so s orbitals and p orbitals are orthogonal. So, but if we are considering s orbital on one ion and p orbital on different ion, they may have some overlap. Their overlap can be non-zero. And in order to avoid mistakes corresponding to this fact, one builds up a matrix of all possible overlaps between all atomic orbitals that we are entering into our computational schematic. And one just uses the letter S and tells this is matrix of overlaps. All orbitals overlap with each other, and most of those elements of this matrix are zero. But just in case, some of them are not, and it should be taken into account. Okay, now electron-electron integrals. So we are not going to develop new theories. We are just humbly using computational software to explore applications. But in case one of us decides to develop theories, one would realize that most of the time one would play with those two electron integrals in one or another form. And one is really getting tired of writing this Coulomb term again and again. So some people replace those terms with pictures, and some people dealing with computational chemistry introduce the shorthand notation. So they are counting orbitals with different indices, R, S, T, U, but one can use some other alphabetical indices, and mention which orbitals are involved in this integral. So there are maximal number 4. Then puts round brackets and agrees on a convention that bra and cat, conjugated and non-conjugated functions, are coming in pairs here and there. And orbitals, atomic orbitals inspected at the same position in space are also placed nearby. So staying with this agreement, using this agreement, one still can represent different types of interactions appearing from electrons interacting to each other. So by swapping the order of those indices, one can represent either Coulomb or exchange terms. And examples are if you use two indices on the left part with the similar indices on the left part and two similar indices on the right side, it will represent Coulomb. And if you have different indices on left and right, this will correspond to exchange. Do not be scared, do not be worried, we are not going to use it for the rest of the course. It is just in case. Okay, so it is what we were talking about all the time. We do have a Fock operator. We act with this Fock operator on one function, one electron molecular orbital, which is unknown by now. And we solve it, we process it as an eigenvalue equation. We are going to find the molecular orbital, and we are going to find the energy of an orbital. And this is a type of problems that we know how to deal with. It is a standard problem of quantum theory. Time independent, one-dimensional, not one-dimensional, single electron equation. Huh? If one applies Fock operator to some arbitrary function, then one will get another arbitrary function. But if the function that you are applying Fock operator to is a good molecular orbital, if it is an eigenstate of the Fock operator, then one will get the same function on the right. So the function is not changed by acting with an operator on it. Okay? And it is very comfortable, very helpful for writing computational programs to recast this equation in the matrix form. So Hartree and Fock stopped here. And the person, his name Roothaan, I don't know how to pronounce it, picked up here and completed the rest of the problem and developed a set of equations that can be solved numerically in an efficient form. So what we are going to do is to replace these unknown functions by their expansion in the basis of atomic orbital. So we are going to plug into this equation into here, right? So this equation is nothing but rewriting of Fock equation with molecular orbitals are replaced by expansion, by their expansion in basis of atomic orbital. So our atomic orbitals are known. We do not need to find them. Those are but our expansion coefficients and energy are unknown. So practically, we need some little trick to eliminate the known atomic orbitals from this equation. So we are looking into some trick to eliminate atomic orbitals. So I think if any of you were attending the advanced physical chemistry, we were already doing this trick for some other systems. So if one does have expansion, and one does know the orthogonality properties of those basis functions, one can simply multiply it by an arbitrary basis function from the left, integrate everything, and then all functions, depending on continuous variable, will be erased. As a result, one will get an equation for coefficients, and it will be a discrete equation. We are using orthogonality. We use the fact that multiplying in most cases, it is just delta function, so it is either 0 or 1. But here, since it is very specific model of a molecule, it can be not delta function, but something more complicated. But in any case, the result of convolution of two basis orbitals can be recorded and saved once and forever for a given molecule. So we do not need to play with it again and again. Record it for the whole computation. Okay, So it is just illustration of what we are doing. So this is Fock operator. This is expansion of molecular orbital in basis of atomic orbitals. And here is our arbitrarily atomic orbital that we are plugging in from the left onto left and right sides of equation, and then we are integrating it over our independent variable so that it will be similar, it will be analogous to bra and cat convolution. So this wave function can be considered as cat, this is cat, and this one can be considered as bra. So we plug in bra here, bra there. And as a result of convolution, we will get rid of those functions completely. Get rid of all functions. Okay. So here is this bra, cat, and here is this bra and cat, right? So there is nothing new, just edit one equation. But we know that those matrix elements, this bra, cat, and operator between them, they are not depending on continuous variable. They're not neither operator nor function, they're just set of numbers. Set of numbers with specific indices. Set of numbers with indices. So this is just some matrix, and this is also some matrix. So let's just have a second look on this. This will be matrix element of Fock operator with indices mu nu, and this will be matrix element of just overlap of different basis functions. S sub mu nu. And we do not have anything depending on R1. We do not have anything depending on position of electron. No dependence on position of electron. So, and then this equation is converting into this form, which is nothing but repetition of this one. And this summation over mute index here and there, it does correspond to multiplication of matrix times vector. Summation over index matrix times vector. So this set of unknown expansion coefficients can be considered as vector, right? This set of matrix elements can be considered as matrix, and then the whole form, Fock equation is converting into algebraic set of equations, matrix equation in algebraic matrix equations. There are no derivatives, there are no continuous variables, just set of matrix by vector. So we do want to find those vectors. We do want to find these energies, and we are going to represent those unknown coefficients in form of a vector. Just for convenience, we can arrange them one after another and say that our molecular orbitals is represented as a vector of expansion coefficient. We are solving a problem to find this vector. And in order to highlight that it is a vector, you can even put the vector sign on the top. Okay, then those Fock operator matrix elements are also arranged in a matrix, and to suppress it, we use the bold space, and overlaps can be also composed into a matrix, and then we just translate Fock equation into the matrix form. And what we are going to get now, it is named not Fock equation, but the person who did it. Roothaan equation. So matrix times vector equals unknown energy, matrix times vector. So this one is Fock matrix. This is vector of expansion coefficients for molecular orbitals. This is energy of molecular orbital. This is matrix of overlaps, and this is again vector for molecular orbital. How do we solve such sort of equations? In course of linear algebra, you have a matrix equation, eigenvalue problem, 2 by 2 matrix. Typically, you take a determinant of such equation and find at which conditions, at which values of this unknown parameter it becomes 0, right? And we do not need to establish this procedure. It was established for many different branches of math, science, engineering. So we just need to, and it was programmed in many ways. So one can go online and just download subroutine for diagonalizing a matrix. It is a very standard problem. So we take Fock matrix, we take overlap matrix, put here unknown energy, and find at which conditions this determinant will be equal 0. And by programming this, one is getting set of eigenvalues. So those are energies of molecular orbitals, and set of vectors representing molecular orbitals. Okay, we are very close to completion of our meeting. So this is the picture borrowed from Wikipedia, but it is just so good that I do not know how to make it better. So it is oversimplified representation of the Hartree-Fock theory implemented for computational problem. So one starts with input of positions of nuclei, and as at the end, one is getting total energy of multi-electron wave function. So in between, one starts from guessing some arbitrary set of molecular orbitals, which can be wrong. We do not need them to be exact. Some guess for molecular orbital, and they are used to build the Fock matrix. So this Fock matrix will reflect the interaction of one electron of interest with the rest of electrons that occupy molecular orbitals that are arbitrarily chosen. Some software packages do smart choice of those initial guesses. Some use just random numbers. And final result is not depending on this. It just may take a little longer computation. Then one is diagonalizing the diagonalizing this Roothaan equation that builds, that forms the energies and expansion coefficients. Then, based on those molecular orbitals, one is building molecular orbitals as function of position, build a Slater determinant out of them, and computes total energy. But this total energy is computed again and again several times, with understanding that when we go again, when we do this iterative procedure, we get a little bit different energy. And the idea of the whole procedure is that difference between previous and next computation of total energy should become smaller and smaller. So one needs also a guess initial guess of total energy. So if previous and next computation of total energy are getting close to each other, it means that we started with good molecular orbitals. We do not need to compute anything else. But if they are diverging, then there is most interesting part. So those molecular orbitals developed through solving the Roothaan-Fock equation are serving to build a new Fock matrix. So the Fock matrix at each step is different. And with help of this new Fock matrix, one is building new set of molecular orbitals. And then, again, forming Slater determinant and finding total energy. And then checking whether present value of total energy is and previous one are getting closer and closer. If they are close enough, then one reports success. If they're not close enough, one uses, again, new last computed molecular orbitals as an input to build Fock matrix. This Fock matrix does depend on what we use as molecular orbital. So this is a price to solve multi-electron wave function. So it is not, this procedure cannot be solved analytically. This is specifically numeric way to solve equations. And the answer is getting improved through each iteration. So these iterations, the values of total energy should get consistent. And the background electric field that affects our single electron should also get consistent. And therefore, this procedure is often referred to as self-consistent field. Procedure. And this idea of SCF is a core for most of computational chemistry methods. It is used not only in Hartree-Fock, but in semi-empirical methods, in density functional theory, and in many others. This is probably most important part of today's meeting. So we have completed
it's about to end.
the subject of Hartree-Fock theory, and I'm here to answer your questions. In case you do not have any questions now, the class is dismissed, and you are kindly and cordially invited into the basement of Arts and Science tonight. Okay. Thank you.
Thank you.
Are you getting enrolled in it?
Yeah.
It's just you two?